Welcome back. My name is Devin King, and in the previous video, I showed you how to generate a power dissipation thermal simulation. Now I will show you how to design a heatsink. First, let's double the number of components on a board, basically the blocks. Select both, and then copy and paste. You will notice that though the block number has doubled, we do not see them. That's because they are currently overlapping. For now, we'll have to move them, but instead of moving them one at a time by changing their point of origin, we'll move them by vector. We have to go to Edit, and then to Arrange, and then Move. Now we can move them by vectors along the X, Y, or Z axis by holding X, Y, or Z on the keyboard. It says this again at the bottom in blue letters. So now select the top of one, hold X, and now I can freely move it in the X direction. If I do not hold X or Y or Z, then as you can see on the left, though I'm only moving it in the X direction, its height changes as well. But it needs to stay on the surface. So hold X and slide it down just a bit. And there we have it. Next, we'll also have to assign thermal energy to the blocks as well. Select both, as done last time. Assign thermal block and 1.5. Now we have 4 blocks and we can now create a heatsink. When generating a heatsink, it'll always appear at the global origin. To change this, we'll have to add a new coordinate system. Go back to Draw, Operations, and Relative Coordinate System. We'll want to put it at the center of the block. And if you remember the dimensions of it, it is a 15 by 10 by 2.1. But if we want it to be above all components, we'll have to include the height of them. Because they're 1 by 1 blocks, we'll have to add plus 1 millimeter. So just click here, and then we'll change the origin here. Into Properties, an origin of 7.5, half of 15, 5, and then height 3.1. And there we have it. It is now at the center, at the height of all items. Now to create the heatsink, go to 3D Components, right-click. We do not have any, so we have to create. You see Fan, Heatsink, and PCB. We'll select Heatsink, and you can already see an outline of the model there. Now we have to name it. It comes pre-named Heatsink 1. If you want to add more information, such as basing this on a real design, you can also include the company name and model number. So you can see here, this is the plane that is currently surface of, the XY plane. Changing this changes the direction of which way it's laying. YZ, ZX, and what we needed in the XY. Its overall height, such as the height of the entire sink, is changed here. We'll put 9.02. Now the length and width is also covers the base. So we'll just give it the same size as the board. Length crosses the x-axis, so that's a length of 15. Width is across the y-axis, that's a width of 10. Now, changing the height of the base does not change the height of the overall heatsink. That is done here. Changing the height of the base, I'll show you. only changes the base and will actually decrease the height of your fins at the top. Relatively, the base is not that thick. It can be around, I would say, 10%. No, even less than 10%, probably around 5% of the height. You can check with other heat sinks you look up online. They will include some of their dimensions. For this one, we'll give it a size of 2.5 millimeters. And this heatsink type, as we can see here, is extruded. You just have 4 pins solid across the board. There is also cut extrusion, which is similar, but now those bars are now separated into single squares, which you can increase in size here in thickness. And then there are cylindrical pins, and now there has cylinders, so the wind, airflow can now move through any direction through them. Extruded is fine to stay with, unless you can choose the crosscut extrusion or cylindrical. We'll double the fin count to 8, thickness of 0.5, and we'll just decrease the base by 1. Make it 1.5 instead. There. This is currently fine for the material for the heatsink fins and base, and we can change it similar to how you change all other elements in the materials, but for now we'll just stick with this. And we'll finish, and there it is. It does come out as transparent, and I'll show you how to change that as well. You must go to Solids, right-click, select all, and then go to Properties. As you can see here, its color is red. We'll give it more of a metallic color. And from transparent, we want opaque. There. Now it is solid. Okay. And now we'll validate the simulation. And I will analyze all. I'll come back to you with the results. And now the simulation has finished. Normal completion on server. And look at this. 88 degrees Celsius. In a previous video, if you have seen, this was in the near thousands. Now it is at a very nominal level, but we can't quite see the model. This can be fixed by hiding the heatsink. Go back to Draw, select the heatsink, and then hide it. It is still there and it is still active, similar to the region, but we just can't see it, and that is fine. Go back to Field Overlays, select Temperature, and now I can see the surface at the junction points between the blocks is what we care about the most. If there is another item on top, we would care about that as well. But between the board and the component is where we're trying to minimize the most amount of heat. 88 degrees Celsius is fine, but with other types of heat sinks, you can get it lower. A second way of adding a heatsink in IcePack is to select from its component library. First, we'll have to just delete the heatsink. And now we have to go to View, go to Component Libraries, and here we have it. You cannot actually see the heatsink until you select it. So if you see one, it's best to look it up online first. And if you don't and just randomly select it, you do not know what you're getting. I'll show you by doing this. It is far too large for the system, but I will still show you how you can still manipulate this. Now you have to go back to the models, select it, right-click, and go to Edit Definition. You can see this name, but now we have to change the plane to XY, and that is fine. Now, we will simulate this again. I'll call you back when I have finished analyzing. Welcome back. And as you can see, with this, well, gigantic for its size heatsink, it is basically stayed at the ambient temperature. Now, as you can see, this is far, far too large of a heatsink for the system. But relative to its contact surface, it decreases the amount of heat that builds up at the junction. Now, in the next video, I will show you how to insert an actual PCB into ANSYS Ice Pack. Thank you for watching.